So that we apparently learned 7.5 and then also like the first order. But then the homework, there's nothing for
Right.
7.5.
Right.
So
Because, so, I mean, obviously I'm not the one who's written this
Yeah.
assignment. Because he's using old stuff, like, so 7.5. Yeah, I don't remember, like, what's different? Yeah. Yeah, I feel like these, like, are those even the right sections from the textbook?
I have no clue because I was
Right.
like so confused about
Right.
this. Because
I-
like he
I
doesn't
know.
put headers to like,
Uh-huh.
sections, so.
Yeah, so I would say, unfortunately, I mean, like, we're gonna cover the differential equation stuff today,
Yeah.
but I mean, I guess I would, yeah. I would say ignore the section 7.5. I don't think that's really like,
So just assume.
right, we're gonna talk about, like, yeah, systems of differential equations. We don't really talk about in this class, like, that's for 17C really.
Right, okay.
Yeah, yeah, so yeah,
Just ignore it.
yeah, I would say ignore it for now.
Okay. Thank you.
You're welcome. We'll get started here in a second. Welcome, everybody. Feel free to fill out the attendance form when you have a second. Here it is again, if you need it. The agenda for today is talking about solving differential equations. So, differential equation, we talked about it a little bit. It's just an equation that has a function. We usually call it y, but really you can call it anything. And one or more of its derivatives. So for example, here's a differential equation. X squared plus 1 times the derivative of y is equal to x times y. So if we want to solve this, well, when you're trying to solve a differential equation, in this class, we have two options. Someone says solve something, solve a differential equation. It's either going to be separable or it's going to be a first order linear differential equation. We're going to start with the separable ones, talk about them. So if something's separable, it means that we can write all of these, I should say, we can isolate dy dx, and then on the other side, all the other things be able to be written as a function of x times a function of y. So if I'm thinking about trying to separate this one, I'm going to first rewrite this as I like to rewrite y prime as dy dx. And I'm going to divide both sides by x squared plus 1 to write this as x times y over x squared plus 1. And then I'm going to separate the x's from the y's, usually only addition or multiplication, or really kind of factoring. So I'm going to say dy dx, and again, I don't think this next step is particularly necessary. We can write this as x over x squared plus 1 times y. So we can really see, oh yeah, there's a function of x multiplied by a function of y. And now that we've gotten the right-hand side written that way, our job is just to bring all of the y's to one side, all of the x's to the other side. And we're only allowed to, at this point, multiply and divide. And we want the y's to end up on the left side and the x's end up on the right side, because we want the dy and the dx to end up both in the numerator. So we can't have the x's come to the left. We have to have the x's come to the right. So what we're going to do is we're going to divide both sides by y, multiply both sides by dx. So we're going to get 1 over y times dy equal to x over x squared plus 1 times dx. And now we have fully separated the variables. The y's are all on one side, the x's are all on the other side. Bless you. After we have separated the variables, that's when we try to solve the system, or sorry, solve the differential equation by anti-differentiating both sides. We're going to take the antiderivative of 1 over y dy equal to the antiderivative of x over x squared plus 1 dx. And we're going to integrate. And we might have to use u substitution or integration by parts or partial fractions or any one of the methods we've already learned for how to integrate things. On the left-hand side, the integral of 1 over y is going to be the natural log of the absolute value of y. On the right-hand side, so we have to do a u sub here. We're going to have u equal to x squared plus 1. du is 2x times dx. 1/2 du is equal to x dx. This is going to become equal to the integral of 1/2 du over u. So I got my 1/2 du as my x dx, and the denominator is u. And the integral of u is going to be, sorry, the integral of 1 over u. I could rewrite this. 1/2 integral of 1 over u du. It's going to be 1/2 the natural log of the absolute value of u plus c. So then the natural log of the absolute value of y is equal to 1/2 the natural log of the absolute value of x squared plus 1 plus c. And if we want to solve for y, we do the e to the stuff. So here's where things are a little bit gross. We're going to say that e to the natural log of the absolute value of y is equal to e to the 1/2 natural log. If I'm dropping the absolute values here, I'll talk about y in a second, plus c. X squared plus 1 is already always positive. We don't need the absolute values there. And then we're going to say that the absolute value of y is equal to, check this out, on the right-hand side, we're going to rewrite this as e to the 1/2 natural log of x squared plus 1 times e to the c. Sorry, I know my 1/2 there looks kind of gross. And yeah, we should really go all the way here. Okay, so we're going to say, so we're going to get e to the c, which we're going to call a. And then this e to the 1/2 natural log of x squared plus 1 is going to be e to the natural log of x squared plus 1 raised to the 1/2. Bringing that 1/2 up as a power, so I can rewrite this as, I'm running out of room, y equal to plus or minus a times e, sorry, oh my gosh, times e to the natural log of x squared plus 1 to the 1/2 is just x squared plus 1 to the 1/2. I know it's really kind of squished in there, apologies. And then we say that plus or minus a is just a constant. It's either positive or negative, so we ignore the plus or minus, so we kind of just let it get sucked up into the a there. And we say that really we're just going to say that y is equal to a times x squared plus 1 to the 1/2. And that is our solution to this differential equation. Notably, there's still a constant in there. And that's typically going to be true of any time you solve a differential equation. if there isn't also an initial condition that then allows you or requires you to go solve for the constant. So the things to observe here, and I'll say this, so kind of after this step here, the rest of this is just kind of gross algebra. It is necessary, but it's not the part you should get wrapped up in so much. The things to really focus on here are, we started off by separating the variables, all the y's on the left, all the x's on the right. We integrated both sides, and then we tried to solve for y. It's not always going to be possible to solve for y, but it's typically usually going to be possible to solve for y. The questions about anything we did here before we do some more examples. And again, apologies for trying to squeeze it all in one page. I should just use all the pages. I know I have lots of paper here. All right, continuing on. Here's another one. Let's say we have y prime equal to x times y times sine of x divided by y plus 1. And we're given an initial condition that y of 0 is equal to 1. So the question we have to ask ourselves is it separable? Well, we've already got y prime by itself. So can we rewrite this equation? I like to write it as dy dx. It's really kind of, especially if you think you're going to separate, you kind of have to write it as dy dx or d whatever, so that you can bring the y's to one side and the x's to the other side. On the right hand side, I'm going to factor this out so that the x's and y's are multiplied by each other. So I'm going to say I have x times sine of x times y over y plus 1. Right, I'm breaking apart the x things and the y things. And then I'm going to multiply both sides by y plus 1 and divide both sides by y to get y plus 1 over y dy, and then also multiplying the dx over to the other side. Get x times sine of x dx. I'm going to say this many times. Once you have dy dx equal to all the other stuff, the only thing you're allowed to do if you're trying to separate is multiply or divide. You can't add, you can't subtract. You can add and subtract before you get to that point, which we'll do, which we'll see in the next example. All right, we've separated variables. Now we're going to solve the system. We're going to integrate both sides. I'm going to rewrite y plus 1 over y as y over y plus 1 over y to make it easier to integrate. And then I have the integral of x times sine of x dx. The left-hand side is not too terrible. We get y plus. So one thing I want to say about the last example, just for one quick second here, is you might have noticed that when I integrated both sides, I had the natural log of absolute value of y. And eventually, so I got down to absolute value of y equal to a times the stuff. And then I said it was plus or minus a. And then I just said, well, plus or minus a is still a constant. We're going to call it a, which means we could have just started off by ignoring the absolute value in the first place, which is what people usually do. But we're really, it's not like we're like breaking a rule or doing something kind of out of sorts. It's totally valid to just ignore the absolute value because of the fact that we can really kind of soak it up into that constant there. So it's hard for me to do because I don't like ignoring the absolute value, but you really can't just say, we're going to say the integral of 1 over y is just the natural log of y without the absolute value, because it's okay to just ignore it. And then to integrate this, we have to do integration by parts. So we're going to let u equal x, our dv is sine x dx, our du is 1 times dx, our v is the antiderivative of sine of x, which is negative cosine of x. And so then when we do this, we're going to get u times v, so negative x times cosine of x, minus the integral of v du, which is minus the integral of negative cosine. Let's just make that a plus the integral of cosine of x dx. And then that's going to end up being that y plus natural log of y is equal to negative x times cosine of x, plus the integral of cosine of x is positive sine of x plus c. And that's our general solution. I will point out here, we can't solve for y explicitly. There's no way to get y plus natural log of y in a way so that we just have y equal to a function of x. And sometimes that's going to happen. Well, not that often, but often enough. We're not quite done though. So this is the general solution, meaning we haven't plugged in our initial condition to get the particular solution. To get the particular solution, we're going to take our initial condition here and substitute in the corresponding values to figure out what that constant is. Now be careful here. If I'm saying that y of 0 equals 1, I'm plugging in x equal to what and y equal to what? What am I plugging in for x? 0. What am I plugging in for y? Right. So be careful. Sometimes people say they want to plug in 1 for y because they can kind of twist it up, but we're definitely plugging in 0 for x, 1 for y. So then I do that, I get 1 plus the natural log of 1 equal to negative 0 times cosine of 0 plus sine of 0 plus c, and then 1 plus natural log of 1, that's a 0. So I have 1 equal to 0 plus c. So c is just 1. I feel like we've seen this problem. I feel like I've seen this problem before. It's like this might have been a homework problem. I don't know. So then our particular solution is going to be y plus the natural log of y equal to negative x cosine of x plus sine of x plus 1. Okay. More. Let's look at this one, which is much less nice looking. X squared times y to the 4th times y prime minus 3 equals y to the 5th. So we haven't encountered first order linear yet, but I will tell you the reason they are called first order linear differential equations, if it was one, is they're first order, meaning that you only have a first derivative, you don't have a second or a third or any higher derivatives, and they're linear in y, meaning if it's a first order linear, you should have a first derivative like a y prime, and then the only other instance of y should be y to the first power. So looking at this, I'm pretty sure it's not first order linear because it's not linear in y. I've got y to powers other than just y to the first. So I'm going to try and separate. I'm always thinking if I'm actually asked to solve it, make sure you read the question, right? Sometimes it'll be like set up something or do something and you don't actually ask to solve it, then it doesn't have to be one of these two things. But if you're asked to solve a differential equation in this class, it has to be one of those two types. It has to be separable or it has to be first order linear. Those are the only two things we learn how to solve in this class as far as differential equations. So here, since it's not first order linear, I'm pretty sure it's separable. So let's try to separate. For the separate, I'm going to first get the 3 over on the other side, and I can add that 3 to the other side just fine. It's totally allowed. I'm going to get y to the 5th plus 3. And then I'm going to, I like to isolate y prime. I just find it to be easiest to see for me that way. So I'm going to write this as dy dx instead of y prime equal to y to the 5th plus 3 divided by x squared times y to the 4th. So I can certainly see that I can pull apart the x's and the y's on the right-hand side. I can write this as 1 over x squared times y to the 5th plus 3 over y to the 4th. Okay, the way I have written this, the y's have to come to which side? The left or the right? There's definitely a right answer and a wrong answer. So here's the left side over here. Here's the right side over here. Which side do I need the y's on? The left side. So I'm going to basically multiply both sides by the reciprocal. Right, you could say you're multiplying by y to the 4th and dividing by y to the 5th plus 3, but we're just flipping and multiplying. So we're going to get y to the 4th over y to the 5th plus 3 times just dy, because I'm also going to multiply the dx over to the other side. And let's write that as x to the negative 2, make it easier to anti-differentiate. So there's my separated differential equation, and now I'm going to integrate both sides. Just so I don't need to write a new line for, but whatever. On the left-hand side, it's looking awfully like oh, sorry, there's a question. We are allowed to split up multiplication in the denominator. We are allowed. Yeah, you can totally split up multiplication in the denominator. Totally valid. Yep. Right? So I'll just say, when you multiply fractions like this, when you multiply a fraction by another fraction, you multiply the top times the top and the bottom times the bottom. So the top times the top is just 1 times y to the 5th plus 3, and the bottom times the bottom is just x squared times y to the 4th, which is exactly what we have over here. So yes, totally allowed. So let's see here. This is a u sub over here. We're going to let u equal y to the 5th plus 3. Our du is 5y to the 4th dy. So I've got a 1/5 du equal to y to the 4th dy. This is looking an awful lot like the integral of 1/5 du over u, which is going to equal 1/5 natural log of u. Yes, I'm ignoring the absolute value. Really, I don't like it. So we're going to end up getting that this is going to be 1/5 natural log of y to the 5th plus 3. So then our solution here is that, well, our integral of both sides is 1/5 natural log of y to the 5th plus 3 is equal to the antiderivative of x to the -2, which is x to the -1 over -1 plus c. Can we solve for y here? Yeah, we can. So we should. Let's go up here and solve it. So we're going to take this. I know I'm all over the place on this page. I'm sorry. And then we're going to multiply both sides by 5. Actually, let's rewrite the right-hand side. We've got 1/5 natural log of y to the 5th plus 3 equal to, let's write that as -1 over x plus c. Multiply both sides by 5. Check this out. We get natural log of y to the 5th plus 3 equal to -5 over x plus 5 times a constant, still a constant. And usually that's what people are going to do. They're just going to say that c is still c. Some people might write like c1 and c2 to differentiate between them, but usually we don't. So if you're multiplying by a constant, it's still a constant. If you're adding a constant, it's still a constant. If you're dividing by a constant, it's still a constant. If you're subtracting a constant, it's still a constant. If you're doing anything else, it's a little bit more involved. But if you're just adding, multiplying, subtracting, or dividing, it's usually okay to just leave it as a c. Then we're going to do e to the both sides. So we're going to have e to the natural log of y to the 5th plus 3 equal to e to the -5 over x plus c. We break apart the right-hand side as e to the -5 over x times e to the c. And then we have y to the 5th plus 3 equal to e to the c is just a new constant. I like to call it a times e to the -5 over x. Finally, subtract 3 and take the 5th root of both sides to get that y is equal to a times e to the -5 over x minus 3. And then it's all of that to the 1/5 power. And we didn't solve for the constant here because we didn't have an initial condition to plug in the solve for. Yeah, we should do that one. That one? Yeah, all right. Just gonna keep doing more examples. All right, so I do have a couple of interesting examples coming up, but let's look at this one before we get there. So let's say let's use some different variables. Let's say we have dl dt equal to k times L squared times the natural log of t. And we're given that L of 1 is equal to -1. This differential equation already has a constant in it. K is a constant, right? My variable is t and my function is L. Definitely not first order linear because it's not linear, right? You've got L squared, right? When you're talking about the linearity, you're always looking at whatever your function is. So usually you're looking at y, but here I'm looking at L, and oh, L squared, not linear. Okay. So also it kind of looks like it's set up to be separated over. So let's bring all the L's to the left and leave the T's on the right. We're gonna have 1 over L squared times DL equal to K times natural log of T times DT. Something I want to say here. Oh, yeah. I would say, so whatever side your function is going on, typically the left, the way I'm always setting these up, you kind of want to have the least amount of stuff on that side as possible. So we could have divided the K over to the left side if we wanted to, but typically if you have the choice, you want to leave as much extra pieces on the right-hand side as possible, not the left-hand side, because you're usually going to try to solve for element. Okay, so then we're going to integrate both sides. We have the integral of L to the -1 DL equal to, let's write this as K times the integral of the natural log of T dt. And that's an L to the -2, not L to the -1. Sorry about that. And the antiderivative over here is going to be L to the -1 divided by -1, which we're eventually going to write as -1 over L. And we're going to put the plus C on the other side. We don't want to put it on the left-hand side. We want to put it on the right-hand side. On the right-hand side, the integral of the natural log of T, we have to do integration by parts. So for the integral of natural log of T dt, we're going to let U equal the natural log of T and dV be dt. Our du is 1 over T dt, and our V is equal to T. So this integral ends up equaling U times V, which is T times the natural log of T, minus the integral of V du, which is T times 1 over T dt. T times 1 over T is just 1. This is really just T times natural log of T minus the integral of 1, which is just T itself. So we get T times natural log of T minus T. So that's what's going over here. You've got K times all of that. T times natural log of T minus T plus another constant C. And now we have to solve for L. So I would rewrite this left-hand side as -1 over L equal to K times all of this. Oh, if we, yeah, there's a couple ways to do this. They're both kind of gross. I would probably take the reciprocal of both sides. So if we take the reciprocal of the left-hand side, we get -L. Take the reciprocal of the right-hand side, you just get 1 over all of that. And then finally, if we multiply both sides by -1, we get L equal to -1 over the same denominator, K times T, natural log of T minus T plus C. And then if we plug in L of 1 equal to -1, so we're plugging in what for what? If L of 1 equals -1, then T equals 1 and L equals -1. So we're going to get -1 equal to -1 over K times T times natural log of T. So that's 1 times natural log of 1 minus 1 plus C. Natural log of 1 is 0. So you've got -1 over -K plus C. What are we solving for? What are we solving for? C, right? So, but it's a little confusing here because there's also the K thing there. The K was kind of already originally in the differential equation, so we're not solving for K unless we're specifically asked for. But the C is the thing that we're solving for when you're plugging in your initial condition. So we're going to get C here. No, I'm not going to say that. So I'm going to take the reciprocal of both sides again, or really just say if -1 equals -1 over some stuff, that bottom stuff has to equal 1. And there's no other choice. This stuff here, right? Yeah. That has to, did I make a mistake? Oh, I did make a tiny mistake. No, I don't like that. I disagree with that. I'm doing this differently. It's fine. I'm going to say that that has to equal 1. So then C minus K equals 1. So C equals K. I like that. I think that's great. So then we can rewrite our final solution Gosh, I feel very messy today. As L as a function of t is equal to -1 over k times t natural log of t minus t plus k. Yeah. Check something here. Yeah, that's totally fine. That's not fine. I am really, wow, I am sorry. Yeah. So let me correct myself before you ask your question. So you might be looking at this and be like, what is James doing over there? James is not really making all the right choices. So this should not have been c equals k. This should have been c equals k plus 1. Sorry about that. Well, well, it does because it's multiplied by 0 minus 1. Right, there's still that -1 there in the parentheses. But yeah, but I blew it here for sure. That should be not c equal to k. That should be c equal to k plus 1. Sorry about that. So then this should really be a k plus 1 over here, not a k. That makes way more sense. And then, so here's what I was doing just now. I was plugging it in. I was like, if I plug in t equal to 1, do I really still get this equal to -1? And I wasn't. I was getting like division by 0, which was a problem. But now if I plug in t equal to 1, I get k times 0 minus 1, which is -k, plus k, which was 0 in my denominator, which is a problem until I added the 1 back in to get 1. And now it's correct. But yeah, I was definitely blowing it there. Something to believe. All right. So let's look at another example. And I think there's a homework question kind of like this. Actually, well, yeah, there is one like this, but I also have the exact one too. So let's look at this interesting question. We're going to solve y prime equal to x plus y. Now I'll point out here, this is a first order linear differential equation. We could solve it using the first order linear process, but we're not going to. We're going to solve it a different way, which is atypical. By making the change of variables v equal to x plus y. So here's how I typically do this. You essentially are saying you want to change this equation to being in terms of v and x instead of y and x. Kind of weird. So if v is equal to x plus y, then the derivative of v with respect to x, because again, we're really thinking that v only depends on x. Yeah, v depends on x and y, but y is meant to be a function of x as well. Right? If you solve this differential equation, we're going to get y as a function of x. So v really only depends on x. So taking the derivative of v with respect to x is sensible. If you take the derivative of this, the derivative of x is 1. The derivative of y is the derivative of y. And then we can isolate y prime and say that y prime is equal to dv dx minus 1. So if we start substituting things in, our y prime equal to x plus y, well, y prime becomes dv dx minus 1, and our x plus y is what we chose v to equal. That's going to equal v. And then this is not super terrible. We can say that dv dx is equal to v plus 1. Okay, this question might sound stupid, but I'm going to ask anyway. Is this equation separable? I should say, is this differential equation separable? Here's why I think this question sounds stupid. I don't have both variables on the other side. If you only have one variable on the other side, it's automatically always separable. You can always do multiplication and division, whatever way we need to get all of the, in this case, v's on the left and x's on the right. So let's bring the dx to the right first. say that dv is equal to parentheses v plus 1 times dx. And then the only option left to me to bring the v's to the left is to divide both sides by v plus 1. Right? We can't just get the v over there on its own. The plus 1 has to come with it. So we're going to write this as 1 over v plus 1 times dv is equal to just dx. And then we're going to anti-differentiate both sides. The integral of 1 over v plus 1 is going to be the natural log of v plus 1. The integral of dx, or 1 times dx if you prefer, is x plus c. And yes, we put the plus c on that side. We're trying to solve for v. We raise both sides as powers of e, so you've got e to the natural log of v plus 1 equal to e to the x plus c. We do the usual thing on the right-hand side. We get v plus 1 equal to e to the x times e to the c. And then we can say that v is equal to, I'm going to call this e to the c a, and get a times e to the x minus 1. Now we're not done, because the original thing wasn't phrased in terms of v, it was phrased in terms of y. Then we have to go back and say, oh, but wait, v is equal to x plus y, which means y is equal to v minus x. So my actual solution is going to be y equal to this v minus x.
I have a question.
Yeah, go ahead.
I might have missed it, but couldn't we also say that y prime is equal to v then? Or
That y prime is equal to what?
v?
Y prime is
X
not,
plus
oh,
one.
oh, I see what you're saying. Yeah, so, yeah, I mean, you're not wrong that y prime is equal to v. But I don't know if that, so, but then, so you could say that, but then you're just going to be saying essentially that v is equal to v, which isn't super helpful. So you're right. It's totally true that, right, if we're saying this is v, then yes, we're saying that y prime is equal to v. But the thing here is that we need to write y prime in terms of x and v so that we can actually go about solving the differential equation. Yeah, but I see what you're saying. Question.
I just want to go in like the beginning, how you go from v equals x plus y to like 1 plus y.
So from here, I took the derivative of both sides. So the derivative of v with respect to x is dv dx. The derivative of x with respect to x is 1. The derivative of y with respect to x is y prime. Or you could alternatively have written dy dx.
It wouldn't just be 1.
It would not just be 1. So when we're in this context here, we are making the assumption correctly that y is a function of x. So we're imagining everything in the situation as being functions of x. X is just itself, y is a function of x, and v equal to x plus y is also a function of x. But yeah, it's kind of like that way back when we did implicit differentiation in 17a, how we were always making the assumption that y was a function of x. And whenever we differentiated both sides, whenever we did like y squared, the derivative was not just 2y, it was 2y times y prime. The same kind of thing is going on here. Let's see the question over here. Where did, they said they got it. All right, cool. All right. Let's look at, there is another problem like this, which I think is a homework problem. I don't really care. Which is the following one. We're going to solve x times y prime equal to y plus e to the y over x by making another change of variable by substituting or changing v equal to y over x. So we're going to do the same sort of thing. We're going to replace every y in this equation with something with v or x in it. Essentially, we don't want any more y's in our equation. All right. Well, gross. I think what might be a smart thing to do, which would be to divide everything by x. If we divide everything by x, things start to look nice. On the left-hand side, we just get y prime. On the right-hand side, we get y divided by x. And sorry, well, it would be nicer if I wrote the right equation down in the first place. The original equation, I'm missing something, I apologize. It's xy prime equal to y plus x times e to the y over x. Sorry about that. So then if we divide everything by x, things get pretty nice. You get y prime, you get y divided by x plus just e to the y over x. And then on the right-hand side, we can start replacing things. Y over x is just v. E to the y over x is just e to the v. On the left-hand side, we have to do a little bit of work. So this is going to be y prime, but we need to replace y prime with what it's equal to. So just like the previous problem where we had that v was equal to x plus y, we took the derivative of both sides. We could do that here and use the quotient rule. That seems terrible. Let's multiply both sides by x in this before we start, oh my gosh, differentiating. So we're going to say that v times x is equal to y. And then we're going to differentiate both sides using the product rule. So that dy dx is equal to the derivative of v times x plus v times the derivative of x, which is 1. And that is going to replace the y prime on the left-hand side of this equation. On the left-hand side, we're going to have dv dx times x plus v times 1 equal to v plus e to the v. Then I think we're on our way. Those v's definitely cancel. We can subtract v from both sides. And then we're in a situation where we can separate variables. dv dx times x is equal to e to the v. I'm bringing the v's to the left, the x's to the right. So I'm going to have a 1 over e to the v times dv equal to a 1 over x times dx. So to get this over here, I divided by e to the v. To get the dx over there, I multiply dx. To get the 1 over x, I divided or multiply both sides by 1 over x. And then we're going to integrate both sides. I'm going to rewrite the left-hand side as e to the negative v. The integral of 1 over x is the natural log of x plus c. We integrate e to the negative v. We get negative e to the negative v equals natural log of x plus c. And the rest is solving for v. So multiply both sides by -1. Take the natural log of both sides, which is kind of grody. You get negative v equal to the natural log of the negative natural log of x plus c. And then multiply sides by -1 again. You get v equal to the negative natural log of the negative natural log of x plus c. And then we're not quite done because we didn't want to solve for v, we want to solve for y. So notably, y is equal to v times x. So there's your v multiplied by x. Sorry, I'm a little out of room here. So we're going to get that y is equal to v times x. So it's going to be x times negative natural log of negative natural log of x plus c. Kind of gnarly. So those are some interesting problems. I feel like this isn't a process we typically use, but there are some hard problems that ask us to do it, so it's worth taking a look at. So when confronted with a differential equation that we have to solve, I would always recommend first trying to see if you can separate variables. But sometimes that's not going to work. So if that doesn't work or doesn't look like it's going to work, then we want to go in a different direction. So the other direction we have is first order linear differential equations. By the way, I saw that Dell sent out an email about like where to find this handout. Is anyone be able to find it? I couldn't find it. I was just curious because like, not that I need to find it, but I want to make sure you all are able to find it. So yeah, I'm kind of curious. It's real quick here. Amelia, you look like you know where it is. Okay. Anyway, it's not, I mean, it's not that important to me, but like, you all should be able to find it. Hopefully. So here's the usual setup. So a first order linear differential equation looks like this. The derivative of y plus some function of either x or t or whatever your variable is times y equal to some other function of your variable. So y prime plus p of t times y equal to q of t, or if you're using x's, y prime plus p of x times y equal to q of x. That first derivative is what's making it first order. This y to the first right here is what's making it linear. And if we're gonna try to do the first order linear differential process, which involves multiplying by an integrating factor, we have to write the differential equation in exactly this format. There is no other way to do it. So let's look at an example. Yeah, sure. So let's say we're given some differential equation y prime plus 3 times y equal to x. Notably not separable. Right? If you try to isolate y prime, let's point out not separable. Right? If you get y prime equal to x minus 3y, and then write this as dy dx equal to x minus 3y, you're now stuck in a place where you can only use multiplication and division, and there's no way to do that, right? I can't divide both sides by x to get the x over to one side, or divide both sides by 3y. It's just not possible. So usually it's really, really impossible to overcome some subtraction thing like this via separation. So since we can't separate variables, we do the other thing. It looks like people are saying they can't find it. Okay, well, I guess I'll send them a message because I feel like you sent that email trying to be clarifying, like here's where it is, and all right, but that's not what we're talking about. So back to this first order linear differential equation. So I will point out that in this differential equation, our p of x is just 3, and not that we really need to write it down, but our q of x is x. And we could get into a little bit more, but for now, we'll just talk about how we do this. So our integrating factor, which some people call mu, some people call capital I. Either notation is fine, but mu is more typical in my opinion. Mu of x is equal to e to the integral of p of x, which in this case is e to the integral of 3, which is just e to the 3x. Especially when we do this, we do not worry about any plus c, any natural log of an absolute value. We're keeping it very, very basic here. So don't worry about any of like the extra little pieces that sometimes you might have to worry about with the integral. Then after you find the integrating factor, so let me say two things. I am imagining Dr. Dedell wants you to show all these steps. I'm pretty sure that's true. But there is kind of a shortcut that you can just jump to the answer after you find the integrating factor. And we'll talk about that too. But for now, let's show all the steps. So the step is to first, after you do that, multiply the equation by the integrating factor. So we're going to take this equation and multiply everything by e to the 3x. So we're going to get y prime times e to the 3x plus y times 3 times e to the 3x equal to x times e to the 3x. Here's the reason why this is great. Whenever you do this, the left-hand side will always end up being the derivative of a product of two functions. Always. In fact, this left-hand side is always the derivative of y times your integrating factor. Always. So in this case, we can rewrite the left-hand side as, check this out, the derivative of y times e to the 3x, our integrating factor. Let's double check that. So if you actually use the product rule to find the derivative of this, you would get the derivative of y times the other stuff, okay, check so far, plus y times the derivative of the other stuff. And the derivative of e to the 3x is exactly e to the 3x times 3. It always works. Why it's done this way, because someone figured out that it always works this way. So then, the nice thing about knowing that the derivative of something is equal to something else is, if the derivative of this is equal to x e to the 3x, then just y times e to the 3x on its own is going to equal the antiderivative of x times e to the 3x. And then we can integrate the right-hand side. It is an integration by parts. U equals x, dv is e to the 3x dx, du is 1 dx, v is 1/3 e to the 3x. We end up getting that y times e to the 3x is equal to u times v, so 1/3 x e to the 3x, minus the integral, and I'm just going to write out what it is here, minus the integral of 1/3 e to the 3x is going to be 1/3 e to the 3x divided by another 3, because we're integrating again. So it's going to be 1/9 e to the 3x. And really importantly here, plus c. And then finally, we divide both sides by that integrating factor to isolate y. So we're going to get that y is equal to 1 over e to the 3x times all of this, including the constant. So it is really important that that 1 over e to the 3x multiplies each of those things, including the constant. You can totally leave it like this. You could also simplify it. If you simplify it, it does kind of look a little nicer. So if we actually distribute the 1 over e to the 3x, you get 1/3 times x, and then e to the 3x over e to the 3x is just 1. And then 1 over e to the 3x times negative 1/9 e to the 3x is just minus 1/9. But then you definitely need the c divided by e to the 3x. If you didn't have, I know. Here. If you didn't have that last part, it'd be really hard to justify that this was the solution. Right? You need that c over e to the 3x. So this is the process for solving a first order linear differential equation. We make sure it's written in the correct format. Y prime plus p of x times y equal to q of x. We find the integrating factor, e to the integral of p of x. We multiply everything by it. We notice that the left-hand side is the derivative of a product. It always will be. And then we say, oh, the derivative of this is equal to that. So the inside stuff is just equal to the antiderivative. Basically, you take the antiderivative of both sides. But the antiderivative of the derivative is just the function inside. And then we integrate and solve for y. Yeah, so someone says, so we take the antiderivative to get the I'm not sure what you've written there. To get the right of the derivative on the right-hand side. Get the what? But yes, we take the to get rid. Yeah. So we're really kind of anti-differentiating both sides. So on this side, the antiderivative of the derivative of this function will just be y times e to the 3x. On the other side, we actually have to do the integration or anti-differentiation to see what it's equal to. So this is the general process. Now, I personally would choose to show this work every time. But some people are perfectly fine with you saying, well, this process always works this way, and the answer always ends up being exactly the same type of thing. So let's actually look at it very generally for just a second. You might not want to write this down. So let's say we're starting off with y prime plus p of x times y equal to q of x. So in fact, here's why this works. If we multiply everything by mu of x, which is equal to e to the integral of p of x. In fact, before we do that, let me ask everybody. If mu of x is equals to e to some stuff, what's the derivative of mu of x? What's the derivative of e to some stuff? E to the stuff times. What's the derivative of the integral of p of x? Let me say that one more time. What's the derivative of the antiderivative of p of x? Just p of x. Okay, so I'm going to write one more thing here. This is really equal to mu of x times p of x, right? Because mu of x is e to the integral of p of x. So the derivative of mu of x is equal to e to the integral of p of x, aka mu of x, times p of x. Okay. Definitely a good time to ask questions if you have questions. So then we're going to multiply both sides of this equation by that integrating factor. So we're going to have on the left-hand side mu of x times y prime plus mu of x times p of x times y equal to q of x times mu of x. But look, this left-hand side is just the derivative of a product. This left-hand side is exactly, in fact, this mu of x times p of x, that is mu prime of x. We just showed it. So this left-hand side really is the derivative of the product mu of x times y. Product rule. Derivative of y times the other thing plus the derivative of the other thing times y. Oh yeah, totally works. The right-hand side is q of x times mu of x. We anti-differentiate both sides to get that mu of x times y is equal to the integral of q of x times mu of x dx. And then finally, dividing both sides by mu of x, we get that y is equal to 1 over mu of x times the integral of q of x times mu of x. Don't be dumb like I was when I learned this and try to cancel those mu of x's. They don't cancel. You have to multiply mu of x by q of x, and then after you've simplified that, anti-differentiate this, and then after you have done that, then multiply it through by 1 over mu of x. I thought I was being really smart back in the day. I was like, oh, but those should just cancel it. No, I was not being smart. I was being super dumb. So, long story short, what I'm saying here is that some teachers, maybe Tamar Galiava, probably not Adele, are cool with you being like, yeah, I found the integrating factor, and now the answer is just 1 divided by the integrating factor times the integral of your q of x times your mu of x. There's still work to be done after this. You still have to actually multiply those things together and then do the integral and then multiply 1 over mu of x, but it is cutting out the steps of showing this product stuff. So I'm still going to show all the steps, but well, maybe I won't do one of them. Let's look at another example. How much time have we got? Okay, we got 20.
Quick question.
Yeah, go ahead.
Sorry. What happened to the e when we found the derivative?
To the e here.
Yeah.
So we found the derivative of e to the stuff and it ended up being e to the stuff times the derivative of the stuff. But then I replaced this. It's not so much that it went away. I just called it by its other name, right? That there is the same as that there, which is equal to mu of x. So I just replaced e to the integral of p of x dx with mu of x, which is what it's called.
Thank you.
You're welcome. So let's look at another example. Let's say we have now, yeah, look at this one. T times y prime minus 4 times y equal to t to the 6 times e to the t squared. So, a couple things to note. It's probably not separable. If you brought this 4y over to the other side via addition and then divided by t, it's looking to be real bad. Also, it's kind of written in a way to suggest to you that this is probably first order linear, right? It's written almost in the right format. What do I need to do to get it so it's actually in the right format? Well, I need y prime isolated. So if you've got a coefficient of y prime, you have to get rid of it via division. So we're going to divide everything by t. So divide by t to get y prime minus 4y over t equal to t to the 6th divided by t is t to the 5th. So t to the 5th e to the t squared. Okay. I don't love the way this is written here. I find it's especially misleading when there's a negative sign there. So if I was rewriting this, I would write it as y prime plus negative 4 over t times y equal to t to the 5th times e to the t squared. The format really has to be y prime plus a function of t or x or whatever times y equal to the other stuff. So there's a minus sign there. That minus sign needs to get kind of soaked up into the p of t. So our p of t here is negative 4 over t. I don't really care that my q of t is what it is. T to the 5th, e to the t squared. It's not so important. So then we're going to find the integrating factor. Our integrating factor, mu of t, is going to be e to the integral of p of t, which is going to be e to the integral of negative 4 over t. Which you all should find right now and simplify as much as you can. You should be getting e to the negative 4 times the natural log of t, and you really don't want to leave that unsimplified here. You want to simplify that as e to the natural log of t to the negative 4, which is then just t to the negative 4. For these integrating factor problems, it is usually pretty necessary to simplify that mu, that integrating factor, as much as you can. So then we're going to skip all the middle parts, but we're going to fill them in a second. So if we skip all the middle parts, you could jump to the answer. The final answer, knowing just the integrating factor here, is that y is equal to 1 divided by your integrating factor times the integral of your q, t to the 5th, e to the t squared, times your integrating factor, which is t to the negative 4th. Which then simplifies actually pretty nicely. This is equal to, well, first of all, let's not write 1 over t to the negative 4th. Let's write t to the 4th. It's usually a pretty good thing to change. And then this integral here, the t to the 5th times t to the negative 4th is just t to the integral of t e to the t squared. Which again would be a u substitution. I'm just going to say what the answer is. It's going to be equal to t to the 4th times the integral of t e to the t squared is going to be 1/2 e to the t squared plus c. If you take the derivative of e to the t squared, you get e to the t squared times the derivative of t squared, which is 2t, which I almost have, because I don't have the 2 there, so I need 1/2 to adjust for that. You could do the u sub, I'm just skipping it. I didn't want to show it. So there is a u sub here. You're getting 1/2 the integral of e to the u, which is then 1/2 e to the u, which is 1/2 e to the t squared. So you could, depending on your teacher, jump to this answer, right? It's always going to be the case that for a first order linear differential equation, if you found the integrating factor, after you set it up right, your answer is just 1 over your integrating factor times the integral of your q of t times your integrating factor. And let's label things here. There's your q of t. There's your mu of t. And here's your 1 over mu of t. But we also could have shown the intermediate steps. We could have taken this equation here and multiplied everything by the integrating factor and had t to the negative 4th times y prime minus 4 over t times y times t to the negative 4th equal to t to the negative 4th times t to the 5th times e to the t squared. And then, so here's the deal. I could simplify this, maybe I will, but I know for a fact that this should be the derivative of the product y times my integrating factor. In fact, here's something I usually do. I just look at this. I look at this like, oh, just move the prime from just being on y to being on the parentheses. So when I think about all this, I'm secretly looking at this and being like, oh, I'm just going to turn that into parentheses t to the negative 4th times y prime. It always works. Kind of cool. I mean, cool. Okay, this is cool for math. All right. So, we're not missing a t squared there. So the derivative of 1/2 e to the t squared is 1/2 e to the t squared times the derivative of t squared, which is 2t, which is giving me that t right there. But I will point out, if you don't love that, you could simplify this a little bit and be like, okay, I have t to the negative 4th times y prime, and then 4 over t times t to the negative 4th is 4 times t to the negative 5th. So that's really a minus 4 times t to the negative 5th times y. And then maybe you're better able to see that, oh yeah, and why am I not writing just t here? Sorry. Right? The derivative of t to the negative 4th is negative 4 times t to the negative 5th. So we really do have a product rule here. I can't say it enough times. It will always be the product rule for that part. That's just always how it's going to work. There is no other choice. So then, great. We get to say that the derivative of t to the negative 4th times y is equal to t times e to the t squared. And if we anti-differentiate both sides, we get t to the negative 4th times y equal to the integral of t e to the t squared. And then we are back over here, where you're going to integrate this and then divide by t to the negative 4th, which is how we get rid of the t to the negative 4th. So I like showing this work because I've done it a bajillion times. But if your teacher says you can just jump straight to the end, then I would probably just do that. But I'm pretty confident that Dell usually likes people to show this intermediate step there. All right. So what about setting some problems up? Like, for example, yeah. Let's do it that way. Sure. Sorry, I like that one, so it's not exactly. Yeah, let's look at this one. So a tank problem. So here's the setup. I'm gonna try not to write all the words because they take time. So tank contains 100 gallons of solution with 10 pounds of salt. And then we're going to add in a solution with a concentration of 2 pounds of salt per gallon. And we're going to add it at a rate of 4 gallons per minute. And then the well-stirred solution. Well-stirred meaning you can assume that the concentration of the tank, that the concentration is essentially was like homogeneous, right? Well mixed, right? Like no matter where you sample from in the tank, the concentration will be whatever the concentration of the tank is. Right. So it's not like it's really salty over here, really not salty over here. The salt level is the same throughout the tank. The well-stirred mixture is drained at the same rate. So then the question is, well, there are many questions here, but the usual starting place is to write and solve the differential equation for this system. So the first and foremost thing we want to do is write and solve a differential equation for the amount of salt in the tank at time t. I'm going to be extra careful here. For the amount of salt. Let's call it S of t in the tank. Almost always when you set up these differential equations, it's always talking about the amount of stuff in the tank, not the concentration of stuff in the tank. So I don't care about the fact that the tank might have a concentration of 20 pounds per gallon. I care that the amount of salt in the tank is 200 pounds of salt, or however many pounds of salt it is. Sure. So always the amount, not the concentration. So first, the setup. So the setup is going to look like this. The rate of change, in fact, let's just write the words. So the rate of change is going to equal the amount in minus the amount out. Very generally, how much salt are we putting in every minute? How much salt are we taking out every minute? So we're going to write that as ds dt, the rate of change of salt per every minute. How much salt are we putting in? Well, we're putting in a concentration of 2 pounds of salt per gallon. So 2 pounds per gallon. And we're putting it in at a rate of 4 gallons per minute. And looks like the units are going to cancel out nicely there. And we're going to have, we're going to put salt in at a rate of 8 pounds per minute. Sorry. Right, the gallons will cancel and you'll have 2 times 4 is 8. So we're putting in 8 pounds of salt every minute, which seems like a lot, but okay. Minus the amount of salt we're taking out. And this is the part where it gets hard, I think. So I want to point out the amount in is the concentration that's going in multiplied by the rate it's going in at. And do the same thing for taking the salt out. We're going to say, well, the concentration going out, this is the hard part. The concentration of salt in the tank is literally how much salt is in the tank divided by the volume of the tank. In the beginning, that's going to be 10 pounds per 100 gallons. But it's not always going to have 10 pounds of salt in the tank. We don't know. The amount of salt in the tank is S of t, the amount of salt in the tank at time t. So my concentration is going to be S of t pounds of salt divided by 100 gallons of volume in the tank. That's the concentration that's going out. And it's coming out at the same rate we're putting it in. So we're draining it at a rate of 4 gallons per minute. or written without all the units, ds dt is equal to 2 times 4 is 8 minus s times 4 over 100 reduces to s over 25. There's my differential equation. The units would be pounds per minute, but we don't really need to put the units on our differential equation. So ds dt equals 8 minus s over 25. And notice it looks kind of like a typical differential equation. You've got a derivative, you've got your variable, your function, not your variable, sorry, and kind of usual thing. And then we're going to solve it. Now, I've always kind of gone back and forth on this question. You could actually solve this one either way. You could solve this one using separation of variables or using first order linear. And while I typically say it's easier to do things using separation of variables, that's not really true. I feel like it's actually easier. Like the algebra is nicer using first order linear. But let me point out how you could approach it either way, because I think it is worth noting. We will do it one way. So if I'm going to solve this, ds dt equal to 8 minus s over 25. If I was going to solve it using separation of variables, I would help myself out by getting a common denominator on the right-hand side. So if I was going to go separation, which I'm not actually going to finish in doing it this way, if I was going to do separation of variables, I would rewrite the right-hand side as 8 times 25 over 25, which 8 times 25 is 200. So it'd be 200 minus s all over 25. And then I would divide both sides by 200 minus s. And multiply both sides by dt. And then integrate both sides. If I was doing separation of variables, that's how I would approach this one. You can make it less good by just dividing both sides by 8 minus s over 25. But here's the not fun part about separation of variables here. You can't just leave that 8 behind. If you're gonna bring all this over to the left-hand side so that the s comes to the left, it has to be all of this. You're kind of stuck. Which is why I wrote it like this and then decided just to bring this over by subtracting. And I know that's an S, that's a 5. I know they look similar. Apologies. Or first order linear. Most differential equations, you won't have a choice. Occasionally you will. So here, if I do first order linear, I'm going to write this as ds dt plus s over 25, or 1 over 25 times s equal to 8. And now I've got my usual setup, my s prime plus a function of t times s equal to a function of t. So my p of t here is 1 over 25. My integrating factor, mu of t, is going to be e to the integral of 1 over 25, which is just going to be e to the t over 25. Not too terrible. We multiply everything by that. So we're going to have s prime times e to the t over 25 plus e to the t over 25 times 1 over 25. Oh, look, the derivative of t over 25. Nice. Times s equal to 8 times e to the t over 25. And then this left-hand side, just like every other time with the first order linear, that's going to equal the derivative of the product, s times e to the t over 25. Remember, if you're me, you're just looking at that first term there and being like, oh, just delete that prime and put it on the outside of the parentheses. That's really, really what I'm thinking. It's not like the actual true math, but like that's the easy way to get there. Like, oh yeah, that term, just take that prime, parentheses, put it on the outside. And then you solve the same thing over here. And then we anti-differentiate both sides. So we're going to get that s times e to the t over 25 is equal to the integral of 8 times e to the t over 25, which is just going to give me that s times e to the t over 25 is equal to 8 times e to the t over 25 divided by 1 over 25, which is the same as multiplying by 25. for 1 plus C, that C is important. And then finally, S as a function of T is equal to, if I divide everything by e to the t over 25, look what I get. This first term divided by e to the t over 25 is just going to be the 8 times 25, which is 200. And then you're going to get C divided by e to the t over 25. So there's our solution, except we have to find C. And we have a minute, so we can do it. So here's our general solution. S of t equals 200 plus C over e to the t over 25. Then if we go back and look at the question, they said the tank has 100 gallons of solution with 10 pounds of salt at the beginning. So that means that at time equal to 0, the amount of salt is 10. So we're going to plug in 0 for t and set that equal to 10. That means that C divided by 1 is equal to 10 minus 200. So C is equal to negative 190. So our actual solution to this system is that S of t is equal to 200 minus 190 over e to the t over 25. Kind of cool. Okay, I know it's 10:20. I'm gonna say one more thing. The thing that I think is really neat about these tank problems, personally, is that as long as you have a tank problem where you're draining at the same rate you're putting stuff in, which I know that sometimes we ask questions where you're draining at a different rate, and those are a little more complicated. But the interesting thing here is that if you let time go on and on and on and on and on, this part here, e to the t is going to get larger and larger and larger and larger and larger, which means this fraction is going to get smaller and smaller and smaller and smaller and smaller. So as time goes on, the amount of salt gets closer and closer to how much? Well, 200 minus essentially something that's very, very close to 0. Okay, that's not the interesting part. The interesting part is that the concentration in the tank, the concentration is going to go towards, well, the amount of salt divided by the volume, which was 100 gallons, which is equal to 2 pounds per gallon. And it is not at all a coincidence that that was the concentration of the thing we were adding to the tank in the first place. If you look back at the original beginning of the problem, we were adding in salt in a solution with a concentration of 2 pounds per gallon. And that is, again, not a coincidence. If you have this sort of situation where you're adding in something at a concentration of 2 pounds per gallon and you let time go on and on and on and on and on, the concentration of the tank will get closer and closer and closer and closer to 2 pounds per gallon, which I just think is neat, but probably not bad. But sometimes you just have to say neat. All right, that's first order linear differential equations. We'll probably talk about it more on Thursday because they can be challenging. And I'll just look actually. If he talks about, if either teacher talks about in class having a tank problem where you're putting in something at a rate of like 4 gallons per minute and taking stuff out at a rate of like 6 gallons per minute, where the rates are different, we should talk about that because it's a little bit more complicated. And you're saying, yeah, you have. Okay, we'll talk about that next time. It's not so much more difficult, but it is a little more difficult to set up and solve. And I'll be over and not drop in C class. And make sure you fill out the attendance form if you didn't already. Scan it right there. Somehow I lost like my other 2 QR codes. I don't know what I like. There's a whole folder full of paper and 2 QR codes that I'd left in some classroom somewhere. I don't know. I've looked all the places I thought it could be. Gone.